Okay. So, in the previous lectures, we have covered metric spaces and norm spaces. In the metric space, what we have seen is that the concept of the notion of the distance between the 2 points on the real line is taken as mod of x minus y, and this concept has been generalized to an arbitrary set x by introducing the notion of the distance t. Then we have, instead of taking this set simply set as, we have introduced the operations and considering the vector spaces V, and then on this vector space we have introduced the concept of the norm, and this norm generalizes the concept of the length of the vector x, In the norm space, we have also seen that we can take any 2 points, and also we can multiply this by x. So, x and y are the 2 vectors. One can add in the norm space the 2 vectors and introduce the norm of x plus y. Similarly, norm of alpha x can be defined, but what is missing here is that in case of the set of all vectors, say x bar, y bar, z bar, there is a well known concept and useful concept that is known as the dot product of the 2 vectors x bar dot y bar. If x bar y bar is suppose x 1, x 2, x 3 in say R 3 space, and y bar is y 1, y 2, y 3, that is also in R 3 space, and this dot product in case of the 3 dimensional vector space is nothing but x 1 y 1, x 2 y 2 plus x 3 y 3. This dot products also leads the another concept which is called the orthogonality of the 2 vector. We say the 2 vectors x n bar and y bar, they are orthogonal if x bar dot y bar is 0. Clear? So, this concept of the orthogonality and concept of the dot product so far has not been generalized from R 3 space to an arbitrary vector space x. So, the question is, can we generalize this concept also to an arbitrary vector space, so that the structure which you are getting will be more useful and can we have a application where the dot product all orthogonality plays the vital role. And this leads to the concept of inner product space, and as a particular case when it is a complete inner product space, we say it is a Hilbert space. Clear? So, idea of introducing the inner product and the Hilbert space basically is to enhance the concept of the orthogonality to a general arbitrary vector space, as well as the introducing the parallel concept or generalized concept of the dot product. Okay. So, what is our inner product space? And Hilbert space. An inner product space or we also call it as a pre-Hilbert space is a vector space together with an inner product, say I am denoting this way, defined on it. defined on it, defined on X is a vector space X with an inner product defined on it. The inner product we will specify, we will define below, just let me complete. And as I told, the Hilbert space is a particular case when we put a certain restriction. So, a complete inner product space, complete inner product space is known as an Hilbert space, known as Hilbert space. Hilbert space. The complete V means that we should have a metric D in terms of the inner product, and under that metric a Cauchy sequence converges. So, completeness means completeness with respect to a metric introduced in terms of inner product. Clear? So, now entire thing which we have defined depends on the definition of inner product. How to define the inner product? Because once the inner product is defined on a vector space, then this pair will be the inner product space, and when we metric is defined in terms of the inner product and every Cauchy sequence converges, then we say it is a Hilbert space. So, inner product is defined as inner product. An inner product on a vector space capital X, say plus and dot, these are the operation. Inner product on a vector space X is a mapping of X cross X to K. K is the field of scalar of the vector space X, because when we say X is a vector space, then there should be a field attached to this. So, X is a vector space over the field K. It may be real, then we say it is a real vector space. When K is complex, we call it as a complex. So, a mapping from X cross X to K, this mapping we call it as inner product, if provided the following conditions are satisfied. So, that is a map, that is with for each, with every pair of vectors x and y, they are associated I scalar. We denote this by, which is denoted as this x comma y, and satisfy the following property. Clear? Means we are having, this is our x cross x, we are having a mapping from x cross x to k. So, pick up at 2 point x and y, clear, say x here and y here, and this is the mapping. So, which will associate this vector to a element, to the scalar x y. Take 2 point x and y, x belongs to x and y belongs to x, and under this mapping we get a scalar x y, which satisfy the following properties. Number 1, that inner product x plus y comma z equal to inner product of x z plus inner product of y z. Second, the inner product alpha x comma y is alpha times inner product x y, where alpha is a scalar quantity belongs to the K set. And third is inner product of x y is the same as inner product of y x conjugate of this. Fourth property, inner product of x x is greater than equal to 0, and if 0, if and only if x equal to 0. So, if these four properties are satisfied, then we say this structure X under this mapping is an inner product space, IPS. Now, let us look what are these properties. The first property and second property, if I combine the first and second property, then what we get is, or remark, conclusion or say remark, remark is, if we take 1 and 2 together, then this implies that alpha x plus beta y comma z equal to alpha of inner product of x z plus beta of inner product of y z. Clear? If I take the third condition, then third shows that alpha inner product of x say gamma y equal to gamma y x conjugate, which is equal to gamma conjugate by x conjugate, which is gamma conjugate x y. Clear? It means that if I take a linear combination in the first coordinate, because this inner product is two coordinate, one and second. So, in the first coordinate, if I take a scalar alpha times x and take this scalar outside, then there is no change. Okay? But as soon as this scalar is available in the second coordinate, the sign is the value changes, it becomes the conjugate of the original one. It means that in the first coordinate the linear property is satisfied, while the second coordinate linearity is breakdown. In fact, it is semi-linear, or because only the conjugate part is there in place of gamma. Otherwise, if we take gamma y, if we take here say inner product of x, say alpha 1 by plus alpha 2 by alpha 2 z, okay, then this can be written as x alpha 1 by inner product plus x alpha 2 z, and that can be written as alpha 1 conjugate x by plus alpha 2 conjugate x z. Clear? It means this alpha 1 and alpha 2 can be taken outside, but there is a conjugate sign. So, it is linear, it is not linear, but we call it such a thing as a semi-linear. So, if we say the result is, or conclusion is, that inner product is linear with respect to first coordinate, while a semi-linear with respect to the second coordinate, or conjugate linear. We can also say conjugate linear. Clear? So, if we combine both in this way, we say inner product is sesquilinear functional. sesquiu linear functional, that is 1.5 times linear functional. Is it clear? Functional means it is value, okay, scalar value. So, this is an example of a sesquilinear function. Okay. Now, what we have, let us go through back again for this. The inner product on the vector space X, we have introduced the concept of inner product. Now, as I spoken that inner product, with the help of inner product, if I introduce the concept of the norm and the metric, then it will be useful, because this inner product will carry the extension of the dot product as well as the orthogonality. So, we define a norm of a vector x belonging to capital X as norm of x equal to inner product x x under root, and metric on x as d of x y equal to norm of x minus y, which is inner product of x minus y under root. We will verify that this is a norm, and this gives you the metric on x. Clear? All the conditions of the norm will be satisfied, except the last one, triangular inequality. We require a Schwarz inequality before going for establishing the triangular inequality is satisfied. So, we will see it later. So, and once it is norm, this will definitely give a metric, because this is defined in terms of the norm x minus y, which is already proved. So, what this shows, that every inner product space is a norm space. Is it okay? And since the Hilbert space is a complete inner product space, so every Hilbert space is a complete norm space, that is Banach space. So, every Hilbert space is a Banach space. The converse of this need not be true, that we will see. However, converse need not be true, that we will see there, that every Hilbert space, every norm space is not a inner product space, every Banach space need not be a Hilbert space. So, that we will see. Now, before going this way, let us see a general results, which we call it as a parallelogram law inequality. The big claim that every inner product space X this satisfy the parallelogram law. Parallelogram law or parallelogram equality, parallelogram law or equality, that is norm of x plus y whole square plus norm of x minus y whole square is 2 times norm of x square plus norm of y square. The physical concept of this is that if we have this parallelogram having say x and y all the sides vectors, then this will represent the vector x plus y, while this one will represent the vector x minus y. So, the sum of the length of this diagonal norm x plus y square plus square of the sum of the length of this diagonal is the 2 times sum of the square of the sides, 2 times sum of the squares of the sides. is it not, x square plus y square. The proof is just simple based on the definition. If we take the left hand side, say norm of x plus y square plus norm of x minus y square, then this is equal to, by definition, norm of x plus y whole square means x plus y comma x plus y inner product, and norm of this is x minus y comma inner product x minus y. Okay. Now, apply this. So, you take this inner product x comma x plus y comma x plus y, then plus x comma x minus y, minus you take it outside because it is a scalar in the first quadrant. So, we get by x minus y, and this will give further x comma x plus x comma y plus y comma x plus y comma y plus x comma x minus, because minus 1 conjugate will be the same as minus because it is real. So, minus x comma y and minus minus plus y comma y. Now, you will see this gets cancelled, by x and somewhere by x is also x minus y. So, it is by x, sorry, this is x, then by, then x minus y, then here minus y x minus y. Okay. Then this we are getting x x and here x by, then by x and by y, then x x x x minus y, then here it is changed minus by x is left out, is it not? So, this gets cancelled from here, and what you are getting is 2 times x x is the inner product is norm x square and by y means norm y square. So, this proves it. Clear? So, what it shows that if a vector space is an inner product space, then it will satisfy, the inner product will satisfy the parallelogram law. It means the norm which is introduced by means of the inner product, that a norm x is inner product x x under root, will satisfy this condition. Clear? If I think other way around, suppose a norm does not satisfy this inner product, then obviously we can say that norm cannot be derived with the help of inner product, because if it is derived with the help of inner product, then it must satisfy the parallelogram law. So, there are examples of the norm space which do not satisfy the parallelogram law. It means those norm space are not an inner product space. Clear? And that gives the counter example that every norm space, that gives an example that every norm space need not be an inner product. For example, if I take say x is CAB, set of all continuous functions defined over the closed interval a b. So, since it is defined over closed interval a b, so it will attain its maximum minimum value, and the norm of x is defined as the maximum of mod x t, and t ranges from a to b. So, obviously, CAB with this norm is a norm space. Clear? Now, we claim that CAB is not an inner product space. Is not an inner product space. Okay? It means the norm which you have taken does not satisfy the parallelogram law. For any x by, this is true for any, this inequality is true for any x by, is it not? Any x by. So, if I take a particular x and y which violate this condition, then obviously this space will not be a null product. So, let us take the class the x and y, choose x t equal to 1, okay, and y t equal to t minus a over b minus a. Both are continuous functions. Okay. So, what is our x plus y? T will be 1 plus t minus a b minus a. What is x minus y t? 1 minus t minus a b minus a. Okay. Now, the maximum value of this is defined as the norm. So, what is the norm of this? Okay. So, the norm of x under this is nothing but 1, because the maximum value of this. What is the norm of y? The maximum value of t minus a over b minus a, t ranges from a to b. Now, t minus a over b minus a, this function by, if I differentiate by prime t, it comes out to be 1 upon b minus a. Clear? So, 1 upon b minus a is positive. So, derivative is greater than 0. So, function is an increasing function. It means its maximum value will attain at the point t is b. So, when t is b, the maximum value of this will be 1. Agreed? Because derivative by is positive. Clear? By prime t is positive. So, by is increasing function, and therefore, we get this maximum value is attained at the point t is equal to b. No. From the Lagrange mean value theorem greater than 0. So, it is a maximum. Okay. So, it is increasing function. Increasing means the maximum value will attain at the end points. Okay. So, b equal to. Now, what is the norm of x plus y? The x plus y, again this is 1 plus, this 1 is okay. The maximum value of this is 1. So, maximum value is means it is 2. Norm of x minus y, the maximum value will be what? What is the maximum value? We are subtracting the things. So, we have to subtract the minimum value, so that you get the maximum. So, minimum value attained when t is equal to a. So, the norm of this will be 1. So, we get 1. So, this is 1, is it not? Now, norm of x plus y is 1, norm of x minus y was 1. Sorry, this is 2, this is 1, and here is 1. So, what we left hand side this thing, this is equal to 5, while the right hand side is 2 times norm x square. This is equal to only 4. So, parallelogram law is not so does not satisfy parallelogram. Therefore, this is not a CAB is not a null product space, though it is a norm space, but it is not a null product space. So, this is one of the example. Another example we can say L2 space, X is L2, okay, or we say LP. Let us take LP, 1 is less than P less than infinity. I take, and the norm of this any point in this LP is sigma mod xi power p power 1 by p, is it not, where x xi1 xi2 etc. This is the elements of LP, and we know this LP with this norm is a norm space. In fact, it is a Banach space also. Okay? This is also a Banach space. Banach space. Now, if we choose x element is 1 1 0 0 0 and let us take the y 1 minus 1 0 0 0. Both are the elements in LP because this finite. So, summation is finite and get clear. Now, if we take x plus y, this is equal to 2 0 0 0 x minus y 0 2 0 0 and they are also in LP. What is the norm? Norm of x under LP, say LP, this is equal to what, 1 or 2 raised to the power 1 by p. xi1 is 1. So, 1 to the power p 1, xi2 is 1. So, 1 plus 1 2 to the power 1 by p, and that is the same as norm of by LP. But what is the norm of x plus y1 p? This is equal to 2 only. You got 2 to the power p power 1 by p. xi1 is 2. So, xi1 to the power p power 1 by p and rest are 0. X minus y, this is equal to what? Same as 2. Now, if I square these two, what you get? So, whole square, this is equal to what? 2 plus 2, 2 square plus 2 square, that is 8. And what is the norm of x square plus norm of y square? 2 times of this, this is equal to 2 times of this square and again this square. So, in fact, 2 into 2 power p. Is it okay or not? Clear? Now, if I want this parallelogram law or equality holds, this is only possible when p is equal to 2. Otherwise, when p is different 2, it will not be satisfied. So, only when p is equal to 2. So, only when p is equal to 2, the parallelogram law holds, but while when p is different from 2, the parallelogram law does not hold. It means that L2 is a inner product space, provided we satisfy maybe an L product space, but LP for p is different from 2 is not an inner product space, but LP is a Banach space. So, again there is a example where so many spaces are there which are Banach, but not a Hilbert, or inner norm space, but not a inner product space. Okay. Now, we will say how this satisfy L2 is a inner product space. We have to introduce the notion of the inner product on L2 suitably, so that all the conditions of the inner products are satisfied. Okay. Let us see how inner product. That is our question. Clear? So, L2 is an inner product space. Clear? What is L2? L2 is the set of those sequence X such that sigma xi square I is 1 to infinity is finite. Clear? If it is a real space, if it is complex, take the mode square is finite. Now, define inner product on L2. So, inner product of x by I am defining as sigma xi I eta I conjugate I is 1 to infinity, where x is xi I, by is eta I belongs to L2. Okay. Now, this may be complex, that is why conjugate is there. Now, this will satisfy all the property of the inner product. First is, if I replace x by alpha x plus beta y, here it will change. So, you can take alpha and beta outside. If I take by alpha here, then conjugate sign is coming. Okay. So, clearly x 1 plus x 2 by that will be equal to 1 to eta I bar, okay, and that can be written as 1 eta I bar xi 2 eta I bar. So, that will be equal to what? Inner product of x 1 by x 2 by. Similarly, if we take inner product of x by conjugate is there, satisfied, is it not obvious? Inner product of x alpha by alpha eta I conjugate. So, alpha bar is coming outside, and that will be equal to, then what is our x x? X x is nothing but sigma xi I conjugate, and that is equal to sigma I equal to 1 to infinity I 1 to infinity mod of xi square. Now, this is positive, and if it is 0, then each of this must be 0, but each one is non-negative. So, individually 0, so equal to 0 will implies that xi I will be 0 for each I. This implies x must be identically theta function. Okay. So, this it means this is an inner product space under this inner product. Okay. And corresponding norm will be xi I square power half, that is the inner product. So, norm of this and norm on L2, norm of x is the inner product of x x conjugate. So, this is equal to what? Under root sigma mod xi square I is 1 to infinity, and that is what we know this. So, it is a inner. So, this is one example. Another examples also are 3 Rn, Rn, Cn. These are also inner product space. Under the inner product defined as sigma xi I eta I bar I is 1 to n, when it is complex number, okay, and we say all verification. There is a space also LPAB. This space also we have discussed, set of all integrable function whose pth integral is fine. So, here A to B set of all functions x such that x t square dt is finite, okay, and the inner product of x by is defined as conjugate. We can just verify it can come. Okay. So, that is completion. If it is so L1 is not in inner product space. L1 is not, a small L1 is not inner product space, except L2, nothing is inner product space. Okay. So, it is basically there is a very small class. The inner product all the Hilbert space is a very small class, which is a subclass of the norm space. Clear? Biggest class is the metric. Then we have excuses to find the norm spaces. Clear? Because every norm space, every metric space need not be norm space. Clear? And from norm space we have further excused as the inner product.
Sir, so if you know that this function is in L1, so we cannot define any inner product?
No, we cannot define. Clear? It should be first the space must be inner product space, then only you can introduce the L2. Clear? So, these are the few examples of the null product space. And now, concept of the orthogonality, we have, let us introduce the concept of orthogonality. In terms of the inner product, orthogonality. An element X, of an inner product space X this, okay, of an inner product space this is said to be orthogonal to an element y belongs to capital X if the inner product of this is 0. Means an X is an set and take element X, then find out the inner product with other elements of X, and if the inner product comes out to be 0, then those elements by 1 by 2 by n we say X is orthogonal to those elements. Clear? Similarly, if suppose X is an element and A is a group of a set of elements, we say X is orthogonal to the set collection A if inner product of X A will 0 for every A belongs to A. Similarly, we define X is orthogonal to, and this is here and denoted as X is orthogonal to Y. Similarly, when we say X is orthogonal to a set A, means that inner product of X A is 0 for every A belongs to A. Or we say the two sets are orthogonal if means the inner product of A B is 0 where A belongs to A, B belongs to B for every pair. For every pair it is 2. So, the concept of the orthogonality can be defined in terms of the inner product. Okay? That's this inner product, this orthogonality will be used, and in fact, most of this charm for the study of the inner product on the Hilbert space is the orthogonality part. Okay? We get the projection theorem, etc. We know the projection whenever any point space is given a point we wanted to drop the shortest distance, it is nothing but the perpendicular distance. So, there is orthogonality comes. Okay. Now, we have introduced the concept of the inner product, and then a concept of the norm is there in terms of the inner product. So, first the inner product, then we have generated the norms, and we have seen that every norm is not an inner product. Now, suppose it is given that this particular norm space is an inner product space. So, the norm space is given, but we do not know what will be the inner product, but it is known this will definitely a inner product. So, can we extract the inner product with the help of the norm of that space? Do you follow me? An inner product is given X inner product, then one can introduce the norm as the norm of X under root X inner product X X. Now, let us think a converse way. If the norm is given, norm of X given, can you find the inner product X X in terms of the norm? Okay, where it is known that this norm space is also an inner product space, or the norm can be derived with the help of the inner inner product. So, this is given by the polarization identity. What is the polarization identity? That in case of the real inner product space, case 1, for a real inner product space, real inner product space X, the inner product X by the inner product X by is given by 1/4 of norm of x plus y whole square minus norm of x minus y whole square. Means a norm space is given, which is also an inner product space, then one can find the inner product of this. This is to discover the inner product, rediscover the inner product from the rediscover, the inner product from the given norm. Clear? So, these norms are known, we can find out the inner product x by, where it is known that this space is a real space, and if the space is complex, for a complex inner product space, the real part of the inner product x by is given as one-fourth of norm of x plus y whole square minus norm of x minus y whole square, and imaginary part of the inner product x by is given as one-fourth norm of x plus I by whole square minus norm of x minus I by whole square. Clear? Now, this can be derived very easily. This norm is given, and it is given that norm is also inner product. So, use the norm x square is equal to inner product x. Open it, you will get these things immediately. So, nothing. So, this polarization identity will help you in rediscovering the inner product, if it is not. Okay. Now, there is one result which we require for establishing the triangular inequality in order to prove the norm. That result is, or lemma is known as Schwarz lemma. Schwarz inequality. It is not a theorem, Schwarz inequality. What he says is an inner product and the corresponding norm satisfy this thing, norm of satisfy modulus of inner product x by is less than equal to norm of x into norm of y, where the equality holds if and only if x by this set is linearly dependent set. Okay. Clear? The proof is simple. The proof of this solves is, so first we are taking 7, this is 8. Suppose one of these term is 0, suppose y is 0. Okay. Then obviously, this inner product of x by equal to less than equal to norm of x, norm of y holds. Is it okay or not? Because 0, it is 0. So, nothing. So, if y is not equal to 0, then let us consider for any scalar alpha, for every scalar alpha, let us have norm of x minus alpha y whole square. Yeah. Norm of x minus alpha y whole square. Now, this norm cannot be negative. So, it is always be greater than equal to 0. Now, this can be written as x minus alpha y comma x minus alpha y, which can be written as inner product x x minus alpha y. So, alpha I am taking out minus alpha y comma x minus alpha y, x x minus x, first is x, okay, and then x with this also. So, plus x minus alpha y, then minus alpha y with this. Okay. So, again x x, here this alpha can be taken outside, we get y x, and when this alpha is taken outside, we get conjugate. Okay. By y, and here it's when alpha is taken outside, we get. Clear? Now, this is equal to conjugate plus alpha bar I take outside, alpha by y minus x y. Is it okay? Now, choose alpha such that this part is 0. Okay? Because alpha is our own choice. Alpha is any scalar. So, if I choose alpha, this means alpha becomes x by over. So, from here we get 0 less than equal to minus x by x over norm of y square. Okay. So, norm by is non-negative. So, what we get, x by x is less than or equal to norm x square norm y square. Clear? But what is this? This is the conjugate. So, we get from here is modulus x into x by means x by mod square, because this is the conjugate is less than equal to norm x square norm y. So, taking the square root, we get the Schwarz inequality. Okay? That is clear. So, this now when it is equality holds,
For other value of alpha, it will not be that.
for other values alpha you can choose accordingly. Suppose I take alpha equal to say suppose 100, then I can pick up the alpha 1 as alpha by 100. okay, so that it gets satisfied. Means we have to pick alpha in such a way, so that this condition is satisfied, clear, because this is what I am saying is a particular case. Okay. For any alpha this is true, this result is true for any alpha. So, I can choose particular alpha such for which this is 0, is it not? That is possible, because that particular alpha also satisfies this condition. So, it will not violate the assumption which we have started, therefore, this. Okay. And when the equality holds, if the equality holds, this must be 0. If the equality holds, then this must be 0. This must be 0 means x equal to alpha y. So, x and y are linearly dependent. So, this. Okay. Let us. Thank you.